Practice homework 9.2, question 1. Using the Laplace transform, solve the following differential equations. First, let's convert this equation into Laplace transform, which means for the A, like Laplace transform, which means d squared plus 3 capital D plus 2 yt equals to Laplace transform of d ft. And since the Laplace transform of the yt is just ys, and dyt, the Laplace transform is as ys minus y negative 0. And for the d squared yt, its Laplace transform is s squared capital ys minus s y minus 0 minus the derivative of the y, the 0 value. And for the ft, which is equals to ut, its Laplace transform is 1 over s. And we can know all this equals to 0, ft ut. So we can eventually get the Laplace transform of the equation is s squared plus 3s, like this, here, here, and here. So s squared plus 2 and ys, and then it's s times 1 over s. So capital S is eventually equals to s squared plus 3s plus 2 and 1 over, and then we just calculate the fs and find its inverse Fourier transform, right? So it's we convert it into multiply F form as 2 over 1, and then it's k1 s1 plus s2 and k2. And similarly, we just do the cover method, and eventually we can get s1 minus 1 over s2. And so its inverse Fourier transform is yt equals to e2 minus t minus e2 minus 2t ut. And this is A. And for the C, for the next question C, we do the same thing, except it has different boundary conditions. So it's just similarly, we just do the same thing except different boundary conditions. So Laplace transform d squared plus 6 capital D plus 25 and yt, and the right hand side is Laplace transform d plus 2 ft. So we do the same thing, because the Laplace transform yt is capital Ys dyt the Laplace transform is s capital Ys minus 1 y0, the initial condition, and d square yt. The Laplace transform is s square ys minus sy negative 0 minus the derivative y 0, and for the ft which is 25 ut, and its Laplace transform is 25 over s. So we can write s squared ys minus sy 0 minus the derivative y 0 and plus 6 s capital Ys minus y0. That's here. And plus 25 ys and equals to s times 25 over s minus f0 plus 50 over s. And then we use the initial condition, which is, since the initial conditions are y0 equals to capital Y, the derivative of the y0 equals to 1, and f0 equals to 0. So we can get s squared ys minus s minus 1 plus 6 times x capital Ys minus 1 and plus 25 ys equals to 25 plus 50 over s. And we get more simplification. Eventually we can get the expression of ys, which is s squared plus 25s plus 50 over s times s squared plus 6x and plus 25. And for this, we just now we convert this problem into just find its inverse Fourier transform, right? So first we can get some simplification is k1 and plus s squared times 6x plus 25, and the denominator is as plus b. And for this part, we use a carve up method. We can get k1 equals to s squared plus 22s plus 50 over s times s squared times 6x plus 25, 1s equals to 0, right? And then this equals to 2, and for this part, so we can get expression of this part. Eventually is ys. We can get 2 over s plus as plus b over s squared plus 6s plus 25. And here we can get we need to use that see that table, and we can get a equals to -1 and b equals to 20 and e equals to 3 and c equals to 25 and b equals to c minus a squared, which is equals to 4. And so eventually the yt for the first part, we just directly get the 2e2 minus t ut, and for second this part we use the Laplace transform pair in that table. You can see the last question, question 2 and question 1, we all see that. So we can get the second part is e2 minus at times a cosine bt and plus capital B minus capital AA over B and times sine bt and ut. And so we just bring all this value to here, we get the final equation, final answer. And this is the first question. And for the next question, find the zero state response V0t of the network in this figure if the input voltage is this one. Find the transfer equation function relating the output V0t to the input ft. From the transfer function, write the differential equation relating V0t to ft. First, let's according to the Kirchhoff laws and the Laplace transform of the different electric components like resistor, capacitor, and the inductor. Let's see the Laplace transform of these components. And for resistor, Vs equals to the R times the current. And for the capacitor, Vs equals to 1 over Cs times current, Is. And for the inductor, Vs equals to Ls times current. So and also let's convert the input voltage into the Fourier the Laplace transform ut. If it's Laplace transform, it will be 1 over x plus 1 square. It's also, you can just check that table. And of course, for the V0t, we can get the Fourier Laplace transform is Vs. So we can use the Kirchhoff law. Hoff's law. We can get two equations. This is two circle, right? Two loop. For first one, so for the first one, if this is I1s, this is I2s, I1s times 1 ohm plus 1 over s times 1 Farad, and minus I2s times 1 over s 1 Farad equals to Fs, which is 1 over 1 plus s squared. And for the second loop, the I2s times 1 over s times 1 Farad and plus 1 ohm s plus 1 omega minus I1s times 1 over s 1 Farad and equals to 0. And so we combine these two loop, and we can get I2s equals to 1 over s plus 1 square s squared plus 2s plus 2. So we write this into two part, right? S plus 1 square plus k2 s squared plus 2s plus 2. And we use the cover up method. We calculate s plus 1 square 2s plus 2 1, and 1 the s equals to minus 1, this part, right? So k1 we can get the 1, and for the k2, let's just combine them together. So now it's x plus 1 square s squared plus 2s plus 2 1, and if we time them together, we will get a very long for this one, s squared 2s plus 2. We will get k1 plus k2 s squared plus 2k1 plus k2s plus 2k1 plus k2. And the k1 we already know it's 1, and after calculation we can get k2 equals to minus 1. And and for the second, this equation, we still need to use we can use a pair, which is a equals to 0, capital B equals to 1, and a equals to 1, and c equals to 2, and b equals to c minus a squared equals to 1. So the inverse Fourier transform I to t will becomes e to t times e to minus t ut, which is correspond to this part. And then the second part, we just use the formula from that table, e2 minus at, capital A cosine bt plus b minus capital A and b sine bt times ut. So a, b, we just bring all this in here. Eventually we get final equations t2 minus t ut minus e2 minus t sine t ut. So now we already know the I to t, which means the current right here. So now we can get V0t equals to the I to t times 1 omega. So V0t equals to 1 omega times I to t, which is the t times e2 minus tut minus e2 minus t sine t ut. This is the final answer of this question. Thank you.